Welcome to episode 6 of Data Every Day. Today we'll be focusing on a CSGO round winner classification dataset. So if we take a look at the data, we can see, actually let me bring this up, make it easier to see. Okay, we have 85 columns, so we have a very good number of features to use to predict the winner of the round. So and we can't see it here, but look, at the end we have a column called round winner, which is basically just whether the terrorists won or the counter-terrorists won. If you ever played CSGO, it's two teams. So basically what we're going to do is start a new notebook as always. Alright, so we'll start by importing our standard libraries, NumPy, pandas, matplotlib, and Seaborn. And then from scikit-learn we'll get a bunch of data preprocessing tools. Label encoder to change our text labels into numerical labels. Robust scaler, which is, it's like min-max scaler and standard scaler for compressing our feature ranges, but robust scaler accounts better for outliers. So since this is a pretty large data set, I think it would be good to use that. We will also be using PCA to reduce the number of features. And lastly, we can get that nifty train test split. Alright, and then our models will just be linear regression, logistic regression, sorry. And we'll use neural net. Alright, let's import. So we'll take a look at the data to start. Just get the file path right here. And data equals pandas.read CSV. And we'll just look at that. And we can see. Alright. So we got a lot of columns. We can't even see them all here. Basically, you can see some of the columns are not numerical values. For example, the maps. So we're going to have to use the label encoder to transform those text labels into number labels. And additionally, we have a true-false column, which that will be a lot easier, but we can just cast that into integers. So it looks like the label column also needs to be encoded. So interestingly, we see at the bottom we have this one row with null entries. So we're going to want to get rid of that. That's not doing anything for us. So let's start by alright, we're going to see, because we don't know if this is the only row in there. We're going to check. So numpy.sum of numpy.sum, this means we're going, here I'll show you why I'm doing this. So if we do data.isNull, it's going to return a matrix that is the exact same data set, except for each entry in the data set, it's going to give us the truth value of whether or not that entry is null. So you see on the bottom we have a bunch of truths because we have null entries here. So we want to do is sum up all the numbers, the number of all null entries in each column. But we can do numpy.sum to sum down across the rows, and then numpy.sum again to sum across the columns. So let's see what that brings us. Alright, so it's saying there's, in the entire data set, there are 83 total null entries. And we notice there's only 85 columns. So that may suggest that this is the only null row in the entire data set. So what we'll do is just drop that row to start. So data.drop, data.columns, and we'll index it at right here, this guy, along the first axis, the row axis, and in place is true. So we run that. Oh, out of bounds. Oh, no. Not columns, index, sorry. There we go. Alright, now we take a look at this, and you see that guy's gone. That null entry at the bottom is gone. So we'll tally up the total number of null entries in the dataset once again, and great, we got 0. So we've eliminated all null entries in the dataset. Now we can move on to working with these guys, these labels, which we want to turn into numbers. So we can quickly see the columns that have non-numeric entries. By checking, so NumPy has, Pandas has a good function, select dtypes, data types. And we can apply this to the dataset to return all the columns in data that have a specific type. And for the type, we go do numpy.number, which will include any numeric type. So if we do this right now, you can see it's going to give us all the columns that have numeric types. What we want is all the columns that don't have numeric types. So we can do data.drop axis 1. And this will give us the dataset with all of these columns dropped. And looks like this. Great, so we have 3 columns with non-numeric entries. Just happen to be the ones we can see right here. These guys. Those 2, and then at the end. Right here. Alright, so let's work on each one. This guy is easy. Bomb planted is quite easy because we can just convert it straight to integers because it's a true-false value. So we can say data bomb planted is now going to be data bomb planted dot as type int 16. Oh, no dot. There we go. Oh, numpy.16, sorry. Okay, now we take another look at this. We can see our bomb planted column has disappeared from this list because now it contains numeric entries. And if we go back to data, we can see bomb planted has been converted to numeric entries. Now for the other 2, these guys, it's going to be harder because we can't just convert it directly. So we're going to use the scikit-learn's label encoder for that. So encoder equals label encoder, and we're going to for the map column, data map is going to be encoder.fit transform a map. So it's going to take in this column, identify how many unique values there are, and then assign a numeric label for each of the unique values. And it's going to transform the data into a new column with numeric labels. Encoder will still retain the dictionary that converts the number to the word, so we won't lose that information. And we can get that information by doing call this map mappings, a new dictionary with an index and a label for index label in enumerate encoder.classes with an underscore. So encoder.classes is a list in order of all the classes that it converted. So because it's in order, the index of the class within the list is the new label, right? Because now it's going to turn it into that number. It's going to turn it into the index within this list. The enumerate is going to give us back the index and the value. And so now we have a new dictionary that takes the index, which is our new label, and the value, which is our old label. And if we take a look at that, mappings, we can see it's a dictionary that converts the index in encoder.classes to the class that it changed from. So now we've already set data, the map column, to be the transformed version of the map column. So if we run this again, we'll see the map column has disappeared. And if we look at data, map is now assigned a unique entry based on this dictionary right here. Okay, let's do the same thing for the other column, which is round winner. So we'll just copy this. Round winner. And we'll call this winner mappings. Alright, so now we check this. Oh no, round winder. Oh, now I have to drop that. And just real quick, you see we've probably added a guy named round winder at the end. So let's get rid of him. Data.drop round winder. One in place. True. Okay. Check back to this guy. He should be gone. He is gone. Okay. So now we do it round winner, map it, and now we check this, and it's gone. So there are no more non-numeric columns in the dataset. So we check back to data. You can see everything in the dataset is now in the form of numbers. So great. What we can do now is scale our data to a range of values that is standard across the dataset. So for that, we will use the robust scaler. As I mentioned earlier, this deals well with outliers. And since this is such a large dataset, we don't want outliers to affect our performance. So scaler equals robust scaler, and x scaler.fit transform x. So this is just going to scale all our. Oh, I'm sorry. We didn't declare x yet. Y is going to be our round winner column, and x is going to be everything else. Alright. So if we just take a look at that, y is a vector of our labels for the round winner, and x is going to be everything except the round winner column. And you'll notice that y is sorted, it seems like. Possibly. Not sure about that, but all zeros at the front, all ones at the bottom. So what we'll do is when we call the train test split function, that will automatically shuffle our data set, so we won't have to worry about that. Alright, so now we're going to scale x to be it will center the means at 0, but it takes percentiles into account. So I'm not sure the specifics, but it's not as vulnerable to being thrown off by outliers as the standard scaler is. So let's apply the transformation, then we can visualize it back in a data frame by checking it afterwards. Okay. Cool. So now all the values are standardized. You can see. Great. So this should be nice and easy to feed right into our data set. Now before we feed it in, just want to consider, okay, this is a lot of data, a lot of columns, 84 different features for, we're just not sure how many of these features are actually useful, how many of these features are redundant. So why don't we check? We'll get the correlation matrix, and we can get a heat map of it. Oh wait, it's not a... Sorry, it has to be a data frame, I think. I think NumPy has one also, though. I should look into that. What? Oh. Let's look this up. Heat map. Should be a rectangular dataset. 2D dataset. What's wrong here? Okay, let's look up the NumPy correlation. Cross correlation. Okay, let's see. X dot correlate. Whoops. What's going on here? It says that... Oh, 2 one-dimensional sequences. Hold on. Pandas correlation matrix. Here it is, .core. That's what I thought. Okay, pd.dataframe x.core. Alright, cool. And then we can pass that in here. So we'll say correlation matrix equals, and then sns.heatmap of correlation matrix. Oh. How is the... I'm confused. Our correlation matrix is 2D, right? Dot shape. Oh. Alright, you know what? I'm not going to waste any more time. I'll look into this and get the heat map working. But in the meantime, basically what we'll want to do is we want to reduce the dimensionality of our dataset, because we have 85 features, but some of them may be redundant. So we can get a good sense of which features are useful using a correlation matrix, but I think we can also use PCA to understand how much data do we really need to retain the same level of information. So PCA, if I did another video on this, but PCA will take all the features and create new features that contain the information of the old features, but in a sort of it condenses them. So the first principal component in the PCA, which is principal component analysis, will have the most information from the old data set. The second principal component will have the second most information, and so on. So what we'll do is we'll get those principal components out of our data set using the scikit-learn PCA function. And the number of components, because we don't know how many we need or how many we want, we're going to make the number of components the same as the number of features. So this is not reducing the dimensionality yet. Right. So we will go ahead and say we'll fit PCA PCA.fit x, and now we can plot these principal components using the PCA has a attribute called explained variance ratio. Explained variance ratio with an underscore. And this is basically just an array of the amount of variance as a percentage that is contained by each principal component. So how much variance from the original dataset is conveyed by each principal component. Now it should sum to 100% across all the principal components, but if we plot this, we could plot it like this. Okay. I guess we'll do, we'll just keep it 10 by 10. And then we'll plot a histogram of this explained variance ratio, and we'll use number of bins equaled number of features. Plot.show. Why is it starting there? What is that? Oh, I don't have that. Okay. Alright, so we can see this tall bar is going to be principal component 1. This little one here, principal component 2, 3, 4, 5, 6, 7, 8, all the way to 84. So it looks like almost 50% of the variance in the original dataset is contained simply from the first principal component. What we want to do is find how many principal components do we need to achieve a certain threshold of variance which is acceptable to us. Because we want to drop a bunch of these. We have 84 of them. We want to get that down to a smaller number while still retaining as much variance as possible from the original dataset. So we'll make a function called getKcomponents, and that'll take in our PCA object and some alpha value, and we'll have an accumulator of the total variance. Set it start at 0, and then for feature and the respective variance in enumerate PCA.explained variance ratio. So what this is saying is in this array of variance ratios, we're going to get the number of that feature, or rather number of that principal component, and the corresponding variance as the value. And each time we will accumulate the total variance. Right, so the variance for this particular feature will be added to the total variance. And remember, this is a percentage. So then if total variance is greater than or equal to 1 minus alpha, return feature plus 1. Okay. And then at the end, if for some reason it doesn't return, we'll just say return the length of this. So it'll be 84. Okay. So what this is saying here, alpha is going to be our threshold of what we accept as a as the amount of variance retained. So we want, let's say, okay, getKcomponents. Let's say we want to use our alpha as 5%. What this is saying is we're going to add up these variance percentages until no less than 5% of the variance, no more than 5% of the variance is lost. So in other words, we're going to add up all the variances until we get at least 95%, which is 1 minus alpha, of the original variance. So if we change this to 0.01, which is 1%, then we would keep adding on principal components until we retain 99% of the variance. So, for example, if I have this at, let's say we'll start out at 1%, 10%. Okay. This is saying we're satisfied with 90% of the original variance, which is 1 minus alpha, right? 1 minus 0.1, which is 0.9. 90%. We're satisfied with 90% of the original variance retained. How many principal components do we need to add together, starting from the first, in order to retain 90% variance? And the answer is 22. We have to add 22 of these guys, and you can imagine them stacking on top of each other, right? Like, so this thing is almost 50. It'll keep going up by adding these on top until we get near 90. As soon as we hit 90, we're good. We only need 22 of them to achieve that. But let's say we want to lower this to 5% instead of 10%. Now we're going to need some more features, because now we want to get 95% variance retained. So you can see we need 28. If we want 1%, so 99% of the variance retained, this is going to go up again, and you can see 41 features. So depending on how picky you are, if you really care about that extra amount of variance, we will make this lower and lower. But I think for our purposes, 5% sounds good, and 28 features sounds a lot more easy to work with, and it's also more computationally inexpensive than working with 85 original features. So we will set this equal to k. So k is going to be 28. Now what we can do is make our x, which is originally, I think our x is still, what is this? Yeah, our x is still just the scaled original features, 84 columns. Alright. So what we'll do now is our x is going to be a transformation of x. So what this is going to do is it's going to take our x, transform it into principal components, but it's going to have all 84 columns. So we'll index it, all rows, but only the first k columns. So now our x will be 28 columns in total. So now we have only 28 features, but we still retain 95% of the variance of the original dataset. So this is very useful for us if you want to reduce the cost or dimensionality of your dataset. Okay, so now we are ready to train. So let's do our classic split. Xtrain, xtest, ytrain, ytest, train test split, x, y, and train size we'll set to 80%. Okay. Now we will train our models. We'll have a logistic model and a neural network model. I'll just put these in there so we can see what's going on. Okay, and we will fit them both. So log model.fit xtrain, ytrain, and we'll do the same thing for the neural net model. Okay. Alright, our logistic model finished. Now it's training the neural network. I think max iterations is set to 200. So it's going to do its best until it finds that the loss is not decreasing enough, or it will continue until the max iterations are reached. So let's just see how long this takes. Shouldn't be too long. Let's see how much is our loss decreasing by. You know, not such a significant amount. It looks like it. It's pretty slow to converge. It looks like. So we might consider increasing the learning rate of this. But for now, you know, it looks like it's doing the best. You know, it's good. You know, it doesn't look like it's really having a problem. So let's see. All right, cool. Oh wait, it has not actually finished yet. Still going. Feel free to skip this part of the video if it's too boring. Should be done any second. I mean, you can't go past 200. I guess we could start on the next block. We'll just be printing the scores. So, print logistic model, and make this an F string. Log model dot score x test y test. Do the same thing with the neural network model, and we can just make it nice to look at doing that. Okay. How much longer we got? Okay, it's done. 200. So that finished. It said it hasn't converged yet, but let's see how it performed. Alright, not bad. Really not bad. For a game like this, in which the win rate of a particular team is roughly 50-50, right? Getting a 70, almost 80% success rate in correct predictions is actually really good, because games tend to, they're not so one-sided. We would definitely not be able to predict 90% of the time, because we can't take into account the human error, the human ability to make a comeback, really. So, based on the stats, in most games, we'll be able to predict the winner successfully. But there's going to be that 30% of the games, 25% of the games, maybe even it looks like 22% of the games, in which the team made a comeback, or it just doesn't. It's not conveyed by the stats alone. So I think these are some really good accuracies, and I think today was quite successful. So thanks a lot for watching. I hope you enjoyed the video. If you did, make sure to leave a thumbs up and subscribe, and comment below to let me know if there's anything I can do to make these videos more interesting or explore new topics. Alright, thanks a lot, guys. See you tomorrow.